entertainment. And yeah, so basically there's different kind of things how we are trying to learn more about the cosmos, right? There are people that are collecting high quality data. Those people are actually not represented at all today. So we will not talk about data collection. Then we've heard about what it takes to understand observational systematics and actual data analyses. So this was, for example, Elizabeth's talk. We've heard about modeling of the late-time universe, both in terms of EFT of the large-scale structure, but also in terms of simulations and emulations, as Fabian and Risa have told us about. Then over the last couple of days, so I think a lot of you have followed this Rise of the Field Theory workshop as well, or actually many participants here are from that workshop. There was a lot of presentations about early universe effective field theory, but also early universe UV complete theories. And yeah, it's kind of interesting to see there's kind of a mirroring here, right? We have EFT in the late universe, which is trying to approximate some UV theory, which would be, well, complete understanding of small scale dynamics and galaxy clustering, galaxy formation. But at the same time, you also have these EFT techniques, and this is actually where they come from, right? In the early universe, in early universe particle physics, but there is the hope that behind that there is actually a UV complete theory. So that's two important aspects that we heard about. And then there is another aspect, which is one way of increasing our knowledge about the universe is just finding a more complete set of statistics, yeah, as opposed to just measuring the variance of density fluctuations as a function of scale, which is what we've been doing in late-time universe for the last 10 years. Is there more efficient ways to extract information? And yeah, you can see all of these different parts of our field are kind of diverging into different directions, it seems, and to some extent this is natural and necessary. But there are also connections between all these different paths. Yeah? Just highlighting a few examples. Early universe and late universe modeling actually inspires each other, especially when it comes to this EFT approach. Then more complete statistics may actually help you to pin down systematic parameters and distinguish them from actual physical parameters. On the other hand, all these higher order statistics, they might actually suffer from systematics that they're not even yet thinking about. So all these problems that Elizabeth told us about two-point statistics might become even worse for that. Then, yeah, higher order statistics help with actually pinning down EFT parameters. You know, there is this thing where you study bispectrum and two-point function together. Then you can actually distinguish between some EFT parameters and some cosmological parameters. And yeah, finally, I want to highlight this early universe, well, I would say the foundations of cosmology, if you will. So sometimes this early universe theory can seem a bit remote from what all the observers are doing or all the people that we heard from today are doing. But as a matter of fact, I think you will be surprised how theory enthusiastic late-time cosmologists and observers are, because the reason why we are doing this, why we are struggling with systematics and with higher order statistics and whatnot, is not because we want to find out more about galaxy bias or something, but because we hope that we uncover new interesting answers, hopefully even UV complete answers about cosmological physics, you know. So the early universe theorists are basically giving us the motivation, I would say, yeah. So yeah, this just to yeah, as kind of some introductory words. And yeah, together with the panelists, we tried to put together this list of different topics that we could discuss today, and which hopefully connect all these different roles in cosmology. And yeah, you guys have voted for this. Yeah, I've put here the three topics that actually received most of the 60 votes, 60 or so votes that we collected in the end. And yeah, these three topics are basically, the first one would be what is still to be understood within lambda CDM. And here lambda CDM really means cosmological constant, cold dark matter and inflation, right? Because this is also one of the building blocks of that model. Is there some generic predictions of that paradigm that we haven't seen yet?
And massive neutrinos.
Yeah, you're right. Yeah, yeah.
Okay, so which we haven't pinned down. Yeah.
Then another question is, what's actually missing for a Nobel Prize for inflation? So is inflation already proven by just what Planck found, that NS is slightly below 1? Would people be convinced of inflation if we still find R greater 0? Or what else do theoreticians actually want to see in the early universe? And how could inflation even be falsified? You know? And other more fundamental problems that come with it. And yeah, so that is kind of the second favorite topic among the people. And then I've put grouped 2 topics together here. Both of them actually 44% of people wanted to hear about this. And this is really, what does theoretical modeling look like in 10 years? So today we've heard about different ansatz. Actually, we've heard about analytical modeling in this EFT framework that Fabian presented. But we've also heard about machine learning approaches, but just learning physics from simulations, or as Risa has told us about, directly emulating cosmological observables from simulations. So what's the kind of theoretical models that we will apply to data in 10 years? And then more focusing on this machine learning approach that is emerging more and more. To what extent is machine learning a black box, and how much can we trust these black boxes? Is there danger of just learning the artifacts in training data, and yeah, can analytical results be incorporated into machine learning? And so this is kind of a topical complex that people also seem to be interested about. So yeah, I suppose, or I propose that we just start from the top of that list. Yeah, you see all the panelists listed here. Yeah, I don't think that they really need an introduction. All are at the very forefront of different parts of cosmology. And I suggest we first make the round through the panelists and see what kind of thoughts they want to share about these topics. And after that, we'll just open up to questions from the audience or comments from the audience. So let's just do it. So among the panelists, I will just go in alphabetical order here. George, do you want to start sharing some thoughts? Oh, you're muted.
Sorry, Oliver. Maybe we should take one point at a time. I mean, there's a lot, you know, this raises a lot of questions, okay? So I think, you know, on point 1.
George, just to interrupt you, I suggest we focus on point 1 now.
Yes, okay. That's right, because you know, you don't want to be brief. I'll give you sort of my perspective of, you know, how to approach cosmology. Okay, you know, that you know, can be misinterpreted as conservatism. Okay, so you know, there's such a rich theory space that there are many possibilities, and you know, the lambda CDM model is clearly an approximation to something, right? But it describes observations remarkably well, but with ingredients that we don't understand. So the thing is that you know, given that there's such a rich theory space, my approach has always been to only sort of get excited if there's some discrepancy with lambda CDM. So we've got a baseline model, and we test it until it breaks down. And so the question is, you know, that's rather than say, you know, specifically going for a particular theory. So there are things about lambda CDM that we haven't understood yet. So neutrinos, gravity waves from inflation, and so on are obvious examples. But it's a good default model, and the question is, are there any tensions in the data which indicate that it might be breaking down? So anyway, so yes.
And
that obviously raises the issue of whether you believe these hints of tensions, like the Hubble tension and lensing and so on and so on.
But apart from just tangents between different probes, is there anything, just any generic thing that you would still need to, like to see that lambda CDM predicts?
Well, as I said, there are aspects that we need to push on, like neutrino masses, like setting limits on R.
Okay, cool. Is that are you trying to say something?
Are we allowed to interfere with the panel?
Yeah, sure, why not?
So are there any tensions, George? What would you say to
that? Well, I wish I knew. So, it's it won't surprise anybody, attending this meeting that I think that the problem with the Hubble tension is, do you believe that the experimentalists working on the distance ladder understand their errors and have estimated their errors correctly? Okay, and I think that there are very good reasons to be very doubtful about whether they have done. With the sigma 8 tension, there is an issue with sigma 8, okay, that bothers me, that isn't widely discussed, and that's that the weak lensing, some surveys like kids and so on are arguing that S8 is low, but yet from redshift space distortions, which are measuring almost the same thing at the same redshifts, there isn't a tension. Okay, so there's and people working on lensing never discuss redshift space distortions. Okay, I think with DESI that problem should be killed, absolutely killed. Okay, with F sigma 8 measurements, and so there is this tension with between lensing and redshift space distortions that exists now, but this problem will be solved in 2 or 3 years with DESI.
George, could I just follow up on that? I agree with what you said, actually, but I'm curious, do you think there's a version where DESI RSD helps us really pin down the low redshift sigma 8, but lensing then and maybe helps us understand if there's a systematic at that redshift in the lensing measurements, and then lensing can add more, or do you think that are you worried fundamentally about the lensing systematics?
Well, I mean, so Risa, that's why I said that I wish I knew the answers to these problems, because you can't second guess.
Sure, me too.
And maybe the lensing people are onto something that's real, okay, and that the problem lies somewhere else. So I just don't know the answer. And it's the same with the Hubble tension, actually. I mean, it's I think they're underestimating their errors, but maybe they're not. I think with all of these things, we do more experiments, more observations, explore theory as well, and see where the patterns emerge. But there are no patterns that are emerging with these tensions. And I think, there isn't anything that, normally there are hints of things. And, like lambda, we knew the parameters of the lambda CDM model before the supernovae, okay? Patterns had emerged from different types of data. And it was kind of, the supernova results clinched, but we knew the parameters beforehand. So there are no patterns like that I see, that I'm aware of right now.
But moving away from tangents maybe a bit, maybe let's hear from our other panelists. Daniel, maybe you can share how you understand the question and what you want to say about it.
Yeah, I think George and the other people who've raised their voices are right that we should be looking for tangents. I would be doing that in a maybe even more non-parametric way. So I wouldn't necessarily be looking at a tension in sigma 8, but a tension in closer to the things that we actually observe relative to predictions that match other observations. And I think from the perspective of structure, cosmic structure, there's really at least 3 dimensions there in which we've only explored a certain regime. There's the dimension of a redshift. You can look at structure at a very early time, at a very late time, and then there's kind of a large blind spot in between. There's the dimension of scale. You can look at structure on more or less linear scales that are still much smaller than the horizon. So that's kind of the range that we're exploring. And you could try to push this research program to smaller scales or even to larger scales. And there's another axis, maybe an integer axis of the kind of statistic you look at, whether it's the power spectrum, the variance of density fluctuations, which is what we've been exploring in much detail. But there's kind of an infinite number of higher order statistical things that you could be comparing your predictions and measurements in. So really in this picture, right, you notice that there's only a fairly limited region of observable things that we've actually compared. And in that small region already, there's reason to be a little bit surprised or a little bit concerned whether there's consistency. At the same time, we should work to expand this region in which we can shed any light with observations and theory. And I think that's what we're all doing, going to smaller scales, going to higher redshift, going to higher order statistics. And so I think the answer to this particular question is, are there still generic predictions to be tested? Emphatically, yes, right? So all these axes, we can go much further than we have. And the answer could be things match, or the answer could be things don't match, right? We really don't know until we've looked.
Yeah, so I'm just going to go through the panel, but anybody just raise their hands if they want to say something else or respond. Shirley, do you have any comments on that?
We can try to attempt, but this is probably swooping around the questions to the theorist, either on the panel or on the audience, whether we're satisfied with, what is lambda and what is, the dark matter candidate truly. And then in addition to, of course, neutrinos, the gravity waves, and also I want to mention the initial conditions of the universe. That's, I think, even though the model fits well, it doesn't really explain, it doesn't lead to understanding of these components yet. So what should we do to approach that direction? What can we do to actually expand our understanding, not just we can fit it? So maybe we need some inspiration from the theorists, because we can build more observational program, but everything we've been doing so far are very, very much what we've done before. So we can push the smaller scale, earlier, larger volume, earlier universe. But is there something that we should do that will give us understanding of these models?
Can you elaborate a bit more about this initial conditions point that what exactly were you thinking about?
I was just thinking about, do we know the actual phase distributions of the early universe? Be interesting to know exactly. I mean, we can describe it with, FNL parameters and GNL and tau NL, but you can as a distribution, or you can describe it as the actual, for each point or an early universe, what are the, overdensity, underdensity exactly.
Cool. Moving on to Slava, do you want to add something?
Not too much, but in fact, actually, I just don't understand why everybody wants tension. If you will get tension, what you will do after that? You see, I have a lot of experience with building of the series. If you will get any tension, I can explain you in 100 possible ways, as you understand then. It also refers to your question, what does it mean to understand what is lambda or CDM? First of all, people have seen this both component in gravitational interaction and not only in CMB, as you know very well, okay? Because they have seen it in supernova, they have seen it in rotational curves, therefore, they are not precisely parameters of the model. It's somewhere there already. It was proven, not even by CMB. If you will forget about CMB, then it's proven by numerous astrophysical observations. Now, again, I can make tens of models for cosmological constant, even with explanation why it's dominating right now, like K essence. I can do it, for instance, with cold dark matter. When people are looking for the particles, why it has to be particle? It can be simplest modification of Einstein equations, for instance, like mimetic matter. But the question is, what can you do, for instance, from the observational point of view to distinguish one model among 1,000 models which really, how it's called, dominating the literature. And in this case, also would be reasonable to answer the question, what does it mean? Do we have understanding? Do we have understanding? What does it mean, baryonic matter? Of course, it consists of something, but right now, cosmological constant and cold dark matter are proven in gravitational interactions. If they will be found, for instance, cold dark matter in the other interactions, I will be happy for the particle physicists, but if they will find nothing, I can give 100 explanations why they found nothing, and it's their problem, it's not my problem. But you know that it's what we have in the nature. Therefore, this lambda CDM, you can call it 6 parameters model fit of CMB data, but I think it's the wrong way of saying the whole thing, because lambda and CDM are there, and it follows from numerous astrophysical data. The fact that they are fitting very well also physical data, CMB curves, I think it's amazing. And if you will get tension, I will be unhappy. You will be maybe happy, because you can imagine what was the state of cosmology 40 years ago, Nobody wanted any tensions. There was complete chaos, if you know, But this we can discuss when we go to the second question, Thank you.
Maybe just a quick follow-up with this, this whole situation that you described, that there is, for any potential models, for any potential tensions, there would be 100 different explanations. Do you think this is a problem, or?
This means, when you have for 100 explanation for something, it means that you don't have real explanation. You see, you can write papers, you can do quite well, but it would not mean that you understood something about nature. You see, because physics is not only exercises with observations and with calculations. It's something like understanding about nature. And I guess that during the last 40 years, we understood quite a lot about universe.
I think, Shirley, you wanted to respond something?
Yeah, this is sort of exactly my, I shouldn't say complaint, but question, right? If we have models that we think, fit really well, but we don't have an understanding, when do we stop, and when will funding agencies stop funding us, I guess, in a practical point of view, and what observations we should try to make to distinguish these thousands of models, I didn't even know there were thousands, that would work to fit the current model.
About finding any agencies, you should not worry, because, okay, there was a great success. By inertia, for next 30 years, you will have no problems with finding agencies.
Shirley, I'm really worried about this, okay, because Lambda CDM is an exceptionally good fit to observational data. Whatever, if it does break down, we I think already know that any deviations are going to be small, from Lambda CDM. But the problem is that there's no guarantee that, in 40 years' time, we'll have found any deviation from Lambda CDM. So it's a question of we have to be lucky.
No, we were lucky, you see, George, but the question is the following. There could be everything in 40 or maybe in 100 years. But let's be realistic. First of all, when people speak about H0 tensions or about sigma 8, you should not confuse, okay, high quality physical data with the data which have a lot of systematics. From my point of view, it sounds even...
I'm not brave to say it in as blunt a way, Slava.
Yes, but I know, but you understand that, okay, we have, for instance, I have a lot of papers in JCAP about this tension, and they are accepted, okay, so what can I do? But nevertheless, people should understand the difference between high quality data when systematic is under control and the data where you have systematics. You see, because there was tension between age of the universe and globular clusters. There was a lot of tensions, as you know. High 130 megaparsec periodicity, if you remember, there was still this thing, and there was a lot of papers written on this topic. Where all these kind of tensions or anomalies are now? Nowhere, you see?
So I'm a little more optimistic than Slava here. I don't have his experience, but I have a higher degree of optimism, both in what would happen if we found a tension and in the credibility of these data that we're collecting. So let's start with the second, because that's what he was just referring to.
Wait a minute. It doesn't mean that I am not optimistic. I am super optimistic because physics worked very well. Yeah. Now, if you will find some tension, for instance, between sigma 8 and etc., then all your data will become the collection of points, because I was discussing with WMAP people in 2003 who were very unhappy not to get big contradiction with the theory. I was telling them, come on, if you didn't confirm the theory, if you would not confirm, then all your data will become the collection of points, which is not quite clear even how to interpret, you see? And the fact that all data came in exact agreement with the theory, this is the most amazing thing, but not, okay, if you would find some tension, for instance, some anomaly in the range of multiple 220, some people even invented some kind of broken inflation to explain 1 point which was down in the first year data of WMAP, not WMAP, precisely. You see, then what you will do after that? You understand your trustability in the understanding what you are really observing will be reduced by many sigmas. Therefore, I am more optimistic than you. You want to find something, okay, what would provide something to do in this field, okay, for the next 30 years. It's okay. It's a different kind of optimism, but certain fields are closed at some point, and the other fields are open.
Understood. I guess my point is here that I would be okay with a situation where we find a tension and you and others come up with numerous explanations for it, and then following other predictions that those explanations make experimentally, right? So that's my understanding of
Okay.
how eventually scientific progress is made, and maybe that's an interpretation of these patterns that emerged that led to the acceptance of lambda CDM as a model that George talked about, right?
Look, if you will take the history during which you were not present personally during last 40 years, there was always tensions. Then tensions disappears. I can tell you until 20 years ago. Okay, for instance, people was pushing this entropy theory of galaxy formation. I have exchanged with him even from 1997. Okay, nobody knew what is going on. When the result started to come and agree with the prediction of the theory, which were in complete contradiction with everything, it made everybody unhappy for some kind of reason. Maybe it made unhappy new generation maybe of people. Yeah, I do not know, but okay.
So sorry to interrupt at this point. I would very much like to hear from our other panelist, Cora. You wanted to comment as well, right?
Yes, so I'm actually a bit surprised since I'm up last. Essentially, my big question is, given that at least I would say 4 of us spend a lot of time on trying to understand nonlinear structure formation, why didn't anyone mention that even if there are no tensions, right? Lambda CDM is correct. I think we can still understand a lot more about structure formation. And if it's just comparing exquisite simulations using machine learning, doing analytical models. So I'm a bit surprised that no one really mentioned this. I think even if everything agrees, this would be a huge success. I think we still haven't really understood, while the cosmic web is so universal, while all of those density profiles look roughly universal in simulations, right? We are making progress of actually simulating phase space soon, which I think is a huge thing. So I think this is one of the aspects in lambda CDM. And I think in large scale structure, I'm also pretty surprised that we never really talk about what the CDM might be. And to connect a bit with the field theory workshop, I think there's still lots of possibilities of effectively cold dark matter, right? That might have wave-like properties or something else. So maybe we should devote a bit more attention to the CDM in the lambda CDM.
I think I agree, and it could be the sort of confirmation that makes Slava happy, even without any tension.
No, you should not distinguish. Lambda CDM is a different field where there could be tensions, there could be great progress, but you have to separate it from the physics of so-called early universe, you see? Because lambda CDM, in a sense of large-scale structure, of course, is not yet worked out, you see, because there you can get hints. What is CDM, for instance, or how lambda can evolve. Even lambda can be not constant, you see. There could be some hints there in this astrophysical data, but it doesn't mean that, for instance, something comes in contradiction with what we learned about early universe from the most pristine data, I mean CMB data, from Planck data, you see. This is difference.
So before we open up to questions from the audience or comments from the audience, let me just summarize a few points that you mentioned so far. So the question is, what is still to be understood within lambda CDM? Yeah? And just a few things that have been mentioned is, for example, neutrino physics. We know that neutrinos are part of lambda CDM, but constraints on neutrino masses are still quite poor. This is something where there's still stuff to learn. We think that if we include inflation as part of this lambda CDM model, then, well, where's the gravitational waves? Also, what about initial conditions, primordial non-Gaussianity even maybe? Phase distribution of the initial density field was mentioned. And finally, Cora mentioned that, and I think Daniel also alluded to this, small scale structure formation. Okay, this is not necessarily fundamental physics beyond lambda CDM, but this question is also not beyond lambda CDM, right? So, but within lambda CDM. And there's lots of predictions on small scale structure formation that we see from simulations or partly also from theory. And yeah, it would be nice to find these. This is how far I understood your answers. So yeah, let's maybe see whether there's comments from the audience. Enrico, you want to say something?
Yeah, thanks. Thanks for setting up a nice discussion here, and thanks to all the panelists for their point of view. Yeah, actually, I wanted to say a couple of things that I find extremely entertaining and kind of important within the context of this. So the question that the game is try to find the most uncertain physical parameter, the most uncertain parameter in science, not just in physics. I'm going to expand it to the whole of science. And I used to think for a long time that the most uncertain parameter in science was the energy scale of inflation, because if you measure in terms of energy, I think you can change it by some 20 or maybe 30 orders of magnitude, depending how much you want to push it. And that, in some sense, it's amazing that the whole mechanism still completely agrees with observation. I think the reason is some underlying conformal behavior. But actually, I think the most uncertain parameter in science is the mass of dark matter. There, it's uncertain by 80 orders of magnitude. You go from supermassive or, well, many solar masses, black holes, to ultralight axions, and there are 80 orders of magnitude. So clearly, there is still a lot that these 4 little letters LCDM are hiding behind, that we have no clue whatsoever about. To me, it's amazing that you can change a physical parameter by 80 orders of magnitude. Like, there is nothing that you can change by 80 orders of magnitude. The other thing I wanted to mention that for me is an important aspect is I think of cosmology as a way to discover both new forces as well as new degrees of freedom. And in some sense, our current consensus on what happened in the very early universe tells us that there was some new degree of freedom, which was not part of the standard model, which was an inflaton responsible for seeding the perturbations in the universe. And we still don't know if there was more than one such degree of freedom, which seems a logical possibility, perhaps not a very appealing one, depending on your point of view. But that's something that perhaps we will be able to answer within this generation of measurements because of squeeze limits of endpoint correlation functions and violation of consistency relations, which if violated automatically tell you that there is more than one degree of freedom in the early universe. And that for me is just like you're at LHC and you see a new bump. So you're detecting a new particle. It's just a one-to-one correspondence. So those are my comments on that. Thanks.
Cool. Thanks, Enrico. Any immediate comment from the panel?
Yeah, I can tell you that there is no immediate new degrees of freedom because you can survive without any inflaton. Okay, you just take A² gravity, and there should be A² term as a result of quantum corrections. Coefficient in front of this A² term is not fixed because you need this thing actually for renormalization of the theory of not even quantum gravity, but normal theory in the external gravitational field. And it's there. Okay, it's some kind of so-called excitation in the deformed vacuum. Now, more or less, moreover, this model is at the moment most favored by observations, as you know, because it gives only 0.3% of the gravitational waves, you see, or even less. It can be even less. No, this model gives 0.3% of gravitational wave. Yeah. And therefore, how you are going to distinguish new degrees of freedom from gravitational degrees of freedom? There is other point also.
I think it's very clear. I think there's a very clear difference. I mean, Lagrangians are not physicals. Particles are physical. And so the way you distinguish new degrees of freedom is by looking at poles in propagators. And the theory you mentioned has extra poles in the propagators that are not gravitons. So it does have extra degrees of freedom. How you write it in terms of operator in a Lagrangian doesn't really matter. The physical existence of new quantum states, that's what means that there is a particle.
Lagrangian is everything what we have. Okay, A² stuff is the collective excitation of the quantized field in the external background. So it can be like phonons, for instance, not necessarily elementary degrees of freedom. It's like in how it's called, solid body propagation of the phonons. And this thing you can never be able to figure out what is there, because you should forget that we have very, very limited number of parameters which we can determine from observations. And we determine practically all of them, because to make better than Planck, okay, maybe actually light bird will be better, but okay, it will not be much better.
Yeah, it's a good point. Yeah, whether they're fundamental or not, that's a much tougher question, whether they exist as resonances. So I agree with that.
So I think Angeran, you also wanted to say something.
Yeah, no, I just wanted to ask a question because maybe I misunderstood, but are you saying that we should like essentially continue to sort of treat lambda CDM separately from the early universe? I feel like that was maybe I misunderstood or misheard, but it isn't a promising sort of point of view is to link our early universe physics to our late universe through things like positivity bounds and such, and even something that Slava you just said regarding R-squared inflation, like that gives us a natural sort of extension to lambda CDM through these, like, well, if you want to class Starobinsky as a modified gravity theory to sort of potentially resolve some of the late universe cosmologies, because I feel like at the moment we're basically treating them as two separate problems rather than thinking about the sort of meeting point between the two.
Yeah, I don't know. I personally consider, I don't know, lambda CDM doesn't really make sense without inflation, right? Or at least in the light of the observational data. But I don't know whether anybody from the panel wants to comment.
The other thing as well is that we're not at the end of inflation as well. That's not really that well understood, right? In terms of the perturbative dynamics that you have in terms of reheating and preheating. Is that something that we should also be focusing on as early universe cosmologists?
Well, you see, concerning reheating and preheating, there should be some observational possibilities to distinguish one model from the other. And concerning reheating and preheating, we will never have such a possibility from cosmology, because for that you need real particle physics model beyond the standard model. And for that you need accelerator. You shouldn't forget that, as Zildovich was saying, universe is a good accelerator, but for poor people. Therefore, if you want to clarify reheating and preheating, you have to go with particle physics, but to the scales which will never be reached on accelerators, if there will be any accelerators in future at all. Therefore, reheating, preheating at the moment is a parameter, okay, encoded in the model. And within uncertainties with which we know parameters, we can never distinguish, for instance, R-squared preheating or reheating in R-squared gravity from phi squared inflation.
So I think at this point we should move on in the list. I know that Shirley actually has to leave in 10 minutes, and which is why I would actually like to jump to the last topic that you see here, which is of most interest to her, I think. And this is, again, what does theoretically look like in 10 years? And how about the credibility of machine learning results? So Shirley, if you don't mind, would you just give your comments and your thoughts on this?
I can start with that. I can try, but I would actually be lovely to hear what theoretical modeling look like in 10 years from other people, because I don't usually do theoretical modeling. My expertise recently have been more application and development of machine learning or deep learning techniques applied to astrophysical challenges that we cannot solve with our current techniques and existing methods. So I think a lot of us have trouble trusting machine learning as like a black box. And this is fundamentally a problem, not just in science, but also in other fields where they always look at it as a black box. But fundamentally, it is a bunch of equations that you apply to the input. So that's one thing. Whether we understand it and what does interpretability or understanding means for everybody is different. It's like if you tell me about wavelet transform, I would have no idea if I haven't worked on it. And for me, it's not understanding or interpretable. For some other people, it might be understandable for them. So I think this is a broader question to ask. Danger learning artifacts of the training data. Yeah, this is something that I think Risa's talk mentioned this too. Like someone asked a question that if we have put in the wrong model, or there are models that we're missing when we're emulating a survey or theory. There are many things you're emulating, right? Either the global latent parameters of the universe, like cosmological parameters or the astrophysical parameters. There is the survey that you also want to emulate, which includes bright stars, weird sky effects, and all that stuff. And you want to emulate the whole thing correctly. If our model is incorrect, what do we do? And it's not just machine learning, it's any model that we do, right? So it's the theoretical bias and the bias we have in terms of our understanding of the survey. I don't think it's specific to machine learning, but this is something I think some new techniques in deep learning have tried to address, which is to look for anomalies. When you look at the survey that you say observe, it can be CMB or 21 centimeter or anything like that, and compare to a generated, observation, does it look different? And you can do that comparison fairly effectively with new techniques in anomaly detection, for example. And people have been able to use this to create, expand your parameter space, basically. So there are other techniques you can also imagine using reinforcement learning or contrastive learning to sort of expand your parameter space as you look at the data, maybe only parts of data, not the whole sky, to improve your model before you actually compare the data and the simulation data. So that's sort of my first spill.
Cool, thanks. Let me just put this question out more generally to the panel and to everybody, I guess. So when it comes to these approaches where people work towards having a machine learning algorithm directly extract cosmological information from the cosmic web, say, yeah, what would your concerns be with such an approach?
So I think we might have to specify what directly extract means. It can mean a variety of things. For instance, you could consider artificial intelligence estimating a parameter in a way that's very much equivalent to a Bayesian statistician estimating a parameter. There's strengths to that approach. There's also weaknesses to that approach that in such an analysis you may miss unexpected signals that are not described by any of the models that are within your prior space. Okay. So I think any sort of criticism there of missing new physics in AI would apply similarly to the Bayesian analysis that we've been doing. You need something in addition to that. You could say that cosmological inference could also be interpreted in a more maybe frequentist way, where you ask, well, does this universe that I've observed look anything like the ensemble of universes that I've expected? And that's a different architecture. That it's a different set of equations, as Shirley described correctly. That's what your machine learning is. It's a set of equations and statistics that you apply to your data. So you could imagine applying, say, a generative adversarial network that can try to distinguish the universe you observe from universes that you simulated with a variety of models or inputs. So ask, am I able to? Does the real universe look different from what I anticipated? So that's a whole another kind of cosmological inference that you might be doing. So I think each of these have their own weaknesses, and they are parallel to the same weaknesses that you would find in traditional statistical analyses of data in a Bayesian or in a frequentist kind of way. And so that's the grain of salt that you will not disappear from interpreting tests of models.
So before we come to any potential response from Shirley, Cora, as somebody who has worked on higher order statistics for a long time, do you think machine learning is going to, I don't know, drive you out of your job by just direct cosmological inference?
Well, hopefully not within a few years. So I think machine learning probably can be helpful even in combination with like summary statistics, but I actually wanted to make a slightly controversial point. If we say what makes the result surprising, I guess it probably means we do some inference on cosmological parameters and it disagrees with what we found with 2-point statistics, right? In that sense, this question then basically gets translated to how much do we trust our current constraints? And I think people like Daniel and George will hopefully say, well, we trust our current cosmological constraints quite a lot, right? So maybe that's a good point to answer for like Shirley.
I'm happy that people brought up all these points. I think there's lots of stuff we're learning about high order statistics from sort of machine learning point of view. We're actually working on a project that looks at expanding the logical structure, the nonlinear evolution part, using deep learning and try to feed back to the theory side, which I thought was pretty cool, that you're combining the understanding of physics and something you don't completely understand in deep learning. And then the other part about, surprising results, I think this is also about our prior in the end, right? What's our prior about all the methods, all the traditional methods, something we have more understanding means we have heavier weight. So we actually put a stronger, confidence in it, basically. And at what point would you switch to say, okay, maybe these other methods will also make sense. And with the BOSS analysis, we did have like very many methods to do even just 2-point analysis. There are many ways to do it. You can have this wedge power spectrum. You can have BAO analysis. You can have, rest space distortions going to different K range. And in the end, all these different answers are within the same error bar, more or less, but they have slightly different results. So this is a question for multi-methods. How do we combine them? And if they disagree with each other, what do you do? I think it's a generic question we have to ask ourselves as a community. I don't have a good answer to it.
I agree with Shirley, and I think people are actually already doing that as well with artificial intelligence, right? Whenever you find something unexpected, whether it's with traditional Bayesian analysis or with artificial intelligence analysis, you're going to look what piece of information actually surprised you among all the data that you've used, and you that is very much possible. It's not a black box in that sense. You can find out what statistic of your data drove that surprising result, and that can lead you to insights on systematics. It can be that you end up not trusting that data. It can lead you to insights on astrophysics, and it can be that you end up not trusting your model or your simulation that predicted that kind of information. But it can also lead to physical insights that you say, oh, it is actually, there's something unexpected here that I think I need to seriously question my theory for. And so this process of looking where the information comes from that led to attention, I think will happen just the same way as it did in the past in a machine learning based analysis as well.
So I was basically wondering, to which extent do you think machine learning is compatible with blinded analyses all the way?
I don't see a fundamental difference. Even in a blinded analysis, right, that can happen. You unblind, you find that your result is unexpected and you want to know why, right? And so then you slice and dice your data to find out what parts of it drove the unexpected result. That doesn't contradict blinding. That's where insights come from, I would say. So I think it's the same kind of logic.
So Shirley, you raised that question yourself. At what point would you actually switch to to the machine learning algorithm and believe the new method? And you said you don't have a good answer, but could you just attempt an answer?
I don't think it's a 1 or 0 thing, right? Because I trust what we understand, our physical intuition. We should trust, all the physics we've learned, and all that stuff would help. And honestly, there's a huge field called like physics-driven ML, where people are applying what we learn in physics. Say, I know that there's physical symmetries like rotational symmetry or translational symmetry, or the fact that if you model gravity waves, black holes merging, these metric have conserved quantities in each single pixel. So that all that stuff can go into the machine learning. That I think it's not a 1 or 0. You have to choose one traditional methods versus the others. I think there's a lot of crosstalk. So I never feel like I need to choose one against the other. And honestly, most of my results, we apply as much physics as we can, and we learn the residual that we don't understand using machine learning usually. So like we do as much as we can push with theory, and then we make the jump, basically. So basically I do what I cannot do otherwise with deep learning.
So George, if you're still on, I know you've also been thinking about these kind of things. What is your take on that?
Well, I mean, so people have touched on, some key points. I mean, certainly, one should never believe results from a black box. You need to know why a particular statistical analysis is giving the result that it's giving. So I think that actually, summary statistics will always be an important part of data analysis. That and you want to know, you want to see the bump. This is the thing that is causing the problem. Okay. It worries me that I mean, my knowledge of machine learning techniques and likelihood-free inferences and so on is based on the astronomical literature, not on any statistical literature. But at least I'm worried that there is a problem, that it's unprincipled. That you have choices, many choices to make on what metrics you use to test things, which are often based on summary statistics, and so it worries me that we don't have a nice methodology yet for actually dealing with these things.
Yeah, I totally agree with George actually on this note. There is a lot to do, and I think people are very excited about it, on sort of combining very traditional statistics like Bayesian inference techniques into deep learning, where if you make a determination of a parameter, say this is a pedestrian on the road, can you give an error bar? Can you have a posterior? And there is a lot of work in Bayesian deep learning direction. There's a lot of work on if you should search all the architecture parameters when you're searching all the nuisance parameters in, say, a surveys analysis. And people are starting to think about that in this direction.
Shirley, these problems exist in Bayesian analysis as well. Mm-hmm. Okay, mm-hmm. I mean straightforward. I mean, there are very, very few situations where you can define a unique likelihood, okay, for a particular set of data. I mean, the idea, Gaussian CMB with simple noise is an example where you can do that at the pixel level. There's no ambiguity. There's nothing else to feed in, okay, and away you go. But when we apply Bayesian analysis, we're making choices. We're doing a Bayesian analysis of a 2-point function, or we can add a 3-point function, or we can add cross correlations, and we're now making choices, okay, and constructing likelihoods where we're making, we've decided what we're feeding in, okay. Now this is unprincipled, okay. So there's a problem, there's a problem with, if you say I've done a Bayesian analysis, what does that, that doesn't actually mean very much. Okay.
I really like what you just said, because that leads to the possibility of doing a full, people like to chaos simulation-based inference, where you actually don't make choices of what summary statistics you put in, and just feed the whole thing through and comparing the simulation and the data. That's not done yet in the full form.
Yes, there's still a problem with that, because what metric do you use? If you use a sort of KL divergence and so on, you don't really know.
That's why there's a lot of work in, they call it multi-bandit, where you actually try different architecture and also try different metric and try different parameters in all the space. This is all very bleeding edge in deep learning, to try to figure out what is the true error when you try. It's like trying all the possible architecture within that RAM. And you always ask, do you try enough architecture? Do you have tuned enough of the hyperparameters? Is this the right metric? And you can try all of them, and there are very significant improvements in trying all these. And there's a huge Google package where they basically search through all architecture possibilities now, called AutoML, where they find the best architecture given a certain metric, and then you ask yourself, what is the right metric? I think the metric should really come from some kind of physical principles in the end, from our perspective. But for the deep learning side, I think they're sort of struggling of, is there a way to make general artificial intelligence where the metric is also determined by the network? And that's sort of a bigger question.
Can I try to bring the discussion one step, to the bigger picture of this question, which we have a relatively theorist-heavy audience here, I think, and in some ways we're making the tacit assumption, which maybe I would subscribe to, that theory is done. At least within Lambda CDM, there's nothing left to do for people with a pen and paper, because we can simulate and emulate, and that is anyway the only way we can improve upon what theorists have already done. Is that something that people vehemently disagree with on the panel or in the audience?
I would disagree, right? Because in some sense, whatever statistics you can learn, it's useless if you can't reliably predict it, right?
But Cora, you and others are so spectacularly successful in predicting, the PDF on any scale of density fluctuations, and so that's all there is, right? Any statistics of density fluctuations follows from that, and baryons, I don't think there's much hope other than ever better simulations informed by astrophysical data. So, what's still left to do for a theorist in a way? So, maybe don't take this as criticism that theory is useless. Maybe take it as an appreciation that theory is really advanced compared to our ability to simulate, gastrophysics.
Well, not that far, maybe. I was actually quite surprised in one of the talks today, where basically the approach was to take an n-body simulation for the gravity part, and then to take an analytic model for the bias part. Usually in my mind, it was always this kind of, we have some hope for predicting gravitational evolution of dark matter only, and then basically everything that's more astrophysical is hopeless. Maybe Fabian wants to make a comment here.
So actually, before we open up for a round of more for a round of audience comments or questions, let me just summarize again what has been said so far. So one thing that Daniel was worried about is, well, in machine learning, it's all about your training set. If there is some kind of physics that you're missing in your training set, then your algorithm will never find it. That was kind of a point. I guess what relates a bit to this is what Shirley said, that there is approaches in machine learning where people are trying to quantify better machine learning results in the sense of error bars. So this is at least how I understood this, Shirley, but please correct me. So for example, if you have some summary statistics, then you can always just compute the chi-square between your model and your data. And if that's really bad, then you know your model is bad, yeah? And apparently there are some sort of metrics that people try to invent for machine learning, which can also tell you exactly that for such a more complicated model. And then you would actually see if you miss physics in your training set, right? So that's a point. Then there was a discussion about can physics be included? Can there actually be like a merger between the two approaches? So can analytical understanding of physics or of symmetries or whatnot actually influence or inform machine learning? And apparently there is approaches and there is some sort of synergy that's there. One big question that's in the room is at what point would we actually trust, say somebody publishes a paper tomorrow, we have analyzed dark energy survey year 3 data with our super machine learning tool, and we find that the 2-point function analysis is wrong or something. At what point would you trust that? What would actually be the criterion to trust that? And what's really bad there is that machine learning often comes across as a kind of black box, and we need to understand more what's going on in the black box. And then what George was criticizing is there's too many choices. There's architectures, there's metrics, it's just so flexible. But then again, Shirley was answering that there is methods of basically almost marginalizing over all your different choices in a sense. And this is just to summarize the stuff. Let's now just move over to a round of questions from everybody else. Jakub, you wanted to say something?
Yeah, I wanted to respond to what I understood as a stipulation from Daniel Gruen, namely that there is allegedly nothing for the theory to do within lambda CDM. But the way I see that, there is a lot to do because it would be great to explain the fine-tuning of the cosmological constant. It would be great to explain theoretically the nature of cold dark matter, and also make some progress on explaining the matter-antimatter asymmetry. So this is all independent from the inflation. I am not even mentioning all the things that we can study and learn from theories of inflation. Right, and also the second remark is about the idea of machine learning as a black box. I think I would agree with George, Efstathiou, and others in namely a machine learning algorithm can be seen as a sort of clever scientist who given some cosmological map can tell us what are the parameters that generated this map. This is one of the applications. But one of the principles in science is that we don't simply trust clever people or clever algorithms, but we want proofs that we can follow. We want algorithmic proofs that we can follow, either on the experimental side, we want an experiment that we can reproduce, and on the theoretical side, we want a theory or a mathematical proof that we can follow with pen and paper, so to say. So I would say it's not enough to just have an output of a machine learning algorithm, so to say.
Cool, thanks, Jakub. Any immediate response?
Yeah, I'll just acknowledge that I totally agree with Jakub and others that, for theory, working on the foundations of what Lambda CDM is and whatnot, definitely that's not what I meant. But for, phenomenological theory, predicting observable signals within some, Lambda CDM model, that's what I was referring to as, maybe we're done.
So before we continue, I just want to quickly think about the timeline. There is another event starting at 6 p.m. We already talked a bit about early universe, but I somehow would very much like to hear Slava's answer on the third question. Let's first give the word to Eva because she has a comment on this topic. But then we should probably move on to the next one. Eva, do you want to say something?
Okay, I mean, I can just be quick and it's not that urgent, but I've wondered for a while the following question. So in primordial non-Gaussianity at the level of, say, 3-point functions, there's been a lot that's been done, but as I understand it, it's been specific to shapes that factorize so that the number of sums over L's and so on in the computations can be done in a reasonable amount of time. So my question is basically, if you try to analyze that instead using machine learning, you generate training data with the non-factorizable shape, and then you'd analyze the data using machine learning. Is that different enough from the traditional approaches that it could actually be done in a reasonable amount of time? I've asked this question to various people before, and the response I get is it's not clear, which means it may be kind of a more specific opportunity for that machinery. So it's just a question I have.
Thanks, Eva. Anybody from the panel who has an idea about this?
Shirley might be the best.
Yeah, Will Colton and I actually are talking about doing this, by the way. So, I mean, not exactly, but very similar ideas. And there are ways to make the likelihood faster to estimate the likelihood properly using something called normalizing flow also, in addition to all these simulation-based inference that you can make it faster. So I'm really excited, but we'll see. We haven't done any work yet.
So did I understand that correctly? Was the question, Eva, whether one could do an inference of more general bispectra, which are not based on just these 3 different templates, basically? Or okay.
Well, yeah. I mean, the problem with non-Gaussianity is it's not only is it more than those templates, it's a functional, right? So the thing that makes me gives me pause is, are we doing it the best way, given that it's, this enormous object theoretically. It's a path integral. It's a functional of early universe fields. So indeed, even at the level of 3-point functions, there are many different shapes. Some of them have been motivated by rather complete theories, and some of those just don't factorize. Some of the leading contributions don't have this special property of factorizing. So could it be that the way you do the analysis in machine learning is faster, and I guess maybe the bottleneck would be the generating of the training data itself. I mean, I don't know, but yeah, the question is, indeed, is the physics is not at all just about the kind of classic 3 templates by any means. And I think on the theoretical side, there's a lot more to do to obtain a useful classification of different types of behaviors that you can distinguish with the data. It's not a matter of every single pseudo theory needing to be tested, but we boil that down to different classes of theories that can be distinguished, and both of these kinds of things, even at the level of 3-point functions, and also all this stuff about what really is the more global shape of the PDF. I could see room for improvement on those. And anyway, yes, long story short, yes, to your question, it's about different shapes in those 3.
Cool, thanks.
Well, if I can jump in here, it's Fabian. If you pursue a forward modeling approach like the one I described, basically then the only thing you need to be able to do is sample from the basically from the wave function of the universe, sample your initial conditions, and then you forward evolve from there. So that's actually a much lower requirement than being able to factorize a bispectra. I mean, it still might be most efficient to come up with a approximate factorizable shape, which, yeah, I don't know if you need machine learning, but you can try to approximate any given shape as using a sum of factorizable shapes. But yeah, so in principle, we just need to be able to sample from that wave function.
Thanks.
Well, thanks everyone. So unless there's any other comments right now, let's just really quickly move to this other question. And so Slava, there naturally you would be the first one to respond to that in case you're still online.
Yeah, first of all, question you have to address to Swedes. I have nothing to do with it. But if you ask me, my personal opinion, NS 0.96 is enough, together with Gaussianity, together with flatness, and what was else there? Yeah, Gaussianity and adiabaticity is more than enough. Also, you should not forget that NS 0.96 is a very non-trivial number, in a sense that is determined, roughly speaking, by the logarithm of galactic scale to the CMB scale. So it's the only formula in physics which involve Planck constant and also gravitational constant. There was the other one, okay, Hawking radiation, but Hawking radiation was never experimentally proved. But 0.96 is the only result in physics which was proved experimentally and which involves both gravity and quantum theory. Now, it's first question. Second question, concerning gravitational waves, their level was never, low bound was never prediction of inflation, because, for instance, in new inflation, you would expect the ratio of tensor to scalar 50 times less than for R² gravity. But after spectral index was fixed, there is a low bound for the ratio of tensor to scalar, and this low bound is precisely 0.3%, no, 0.5%, like in R² gravity. On the other hand, having uncertainty, I mean, like 3 sigma uncertainty in the value of spectral index, you can reduce this low bound by factor 7 easily. If, of course, you would have infinite sensitivity, you could rule out the whole thing. But I think actually it will never be reached just simply because of limitation from observations. Now, therefore, if we will find gravitational wave, will be perfectly fine with light bird. If we will not find them, it would not tell us anything. You see, it will not rule out, it will not falsify any theory. Okay, it will not tell us that we live in a chaotic universe. Now, does inflation solve initial condition problem? Of course it solves. It solves because you just postulate very simple things, that there was exponential expansion and with graceful exit, and you do not have any headache anymore. You are producing everything from one causally connected region. Now, multiverse is some kind of, I'm sorry, extension of the particular models beyond the range of their applicability, what I would say. You see, because I could modify all this kind of potential in such a way to avoid, first of all, fine-tuning problem, and second thing, to avoid multiverse problem. Because if you do multiverse in the sense of reproduction, then of course you are getting complete non-predictability. But it's not question to me, it's question to philosophers or to the people who love just to discuss the things without formulas. What can I say? But as I said, okay, multiverse is not inevitable consequence of the existence of initial inflationary stage. You see? Okay, so it's a short answer.
Yeah, thanks a lot, Slava. That was very, very concise. Any response by anybody? And yeah, I should say, really, yeah, the first question didn't do the thing justice. You're right. Yeah, there's also the Gaussianity and adiabaticity and what you mentioned. Yeah.
No, the last time when inflation could fail was this kind of non-Gaussianity measurement. You see, because people spreaded the rumors that FNL would be 400. I said that if it's 400, then it means that forget about series. You see, because of course I can also build 400, okay, in the so-called complicated model with two fields or some kind of junk like curvaton if I will use or whatsoever. But inflation is the minimal configuration, P is equal minus epsilon with little deviation from this equation of state, is the best effective theory of the earlier universe without referring to underlying models with curva, with scalar field or with R squared or whatsoever. This is enough for observations. And this only thing, in conditions that there should be graceful exit, smooth graceful exit, also gives you number 0.96. So better to say smaller than 0.97. You see, I had actually, in 2003, I had exchange of messages with Lyman Page, because when there was no spectral index, and he wrote to me, if they will find 0.99, could I throw out the toil on inflation? I told him, no problem. You see, if you will find it, okay, with plus minus 0.01 at the level of 3 sigma, then, okay, the theory as predictive theory will be dead. Of course, everybody, you can explain everything, yeah, as you know, introducing new and new parameters. But when you have one parameters and 4 predictions is not the same story when you have 4 parameters and 1 prediction. One thing is real, have something to do with nature. The other is so-called theory.
Could I make a comment?
Please, George.
Yes. Okay. So, I mean, Slava said that you know, these problems of measure and multiverse are really, you know, problems for philosophers. I think that's only because we're nowhere close to having the you know, the machinery to tackle these problems. So I think that they are real problems, and maybe one day we'll be able to solve them, but we're not close to solving them now.
No, George, I told you it depends on the extension of your model to high fields.
No, of course, that's what I mean. That's what I mean.
I have no multiverse.
No, but no. Look, but the thing is that you could also imagine, you know, I'm not scared of the multiverse, okay? And the measure problem in the multiverse is a soluble problem, okay? That's also a possibility. So we don't have to abandon the multiverse just because it poses problems. There may be solutions to these problems, but we're not close to it. So, and it's in that sense that we're not close to having a solution to the measure problem, that it is in the realm of the philosophers. So I totally disagree with people like Steinhardt that use these kinds of arguments of naturalness and, you know, so on, and initial conditions of inflation to argue against inflation. I don't think that you know, that you can make that sort of argument credibly. Okay. The other point is that often I think it helps you know, one's thinking to say, well, you know, there is this problem. What would be the consequence if we solved it? Okay. And I don't think it would make much of a difference, okay, if we had a solution to the measure problem. What it would tell us is whether we're in a more common region of the multiverse or in a, you know, special region of the multiverse. I don't actually see that helps us in solving problems in cosmology, to know that. I mean, it's like saying that you know, well, you know, we should all be Chinese because there's more Chinese than anybody else. But somebody has to come from Iceland, okay? So, you know, if I come from Iceland, you know, I'm happy with that, even though it's, you know, I'm in a small minority of the human population. So it doesn't help us to have a solution, actually. What we want from theory is, and this is solvable without tackling having a solution to the measure problem, is understanding correlations between different types of things, different observables, and so we could make progress on that without solving the measure problem. So,
I agree 100%.
So yeah, given that this other event is about to start, we unfortunately have to wrap up here, but this was a really interesting discussion. Thanks a lot to all of the panelists for contributing, and everybody else who either listened or contributed to the discussions. Thanks a lot for being here. Yeah, regarding the Cambridge LMU workshop,